This video will cover a full review on Unit 2, which is on scatter plots and linear regressions. In our first example, we're looking at a colony of sparrowhawks, and in particular, we're looking at what percent of this colony is made up of birds that have returned from a previous year and what percent are new birds. We're going to start off by making a scatter plot in our calculator. So we would make two lists in our calculator, set up the scatter plot, and we would see this graph right here. Now we want to describe the association, and when we do that, we want to use the acronym FUDS. F is for form. That is approximately linear for this graph. U, unusual features. There's no outliers. Direction, this is heading downhill, so it's negative. And strength is measuring how well does this data fit a line of best fit. Let's call this one moderately strong. So we would write something like this: the association between percent of sparrowhawks that return each year and the percent that are new to the colony is negative, that's the direction, linear, that's the form, moderately strong is the strength with no apparent outliers. We also want to finish with a statement saying something like, generally speaking, the higher the percentage of returning adult birds, the lower the percentage of new adult birds. So now we want to create this line of best fit by running a regression on those two lists there. We'll do it on our calculator, and it'll give us this output right here. We're asked what's the correlation coefficient, and that's the R value down here, so negative 0.748. And what's the least squares regression line? We take the A, which is the intercept, and the B, which is the slope, and plug it into this equation. Remember, we always want to put a hat on the Y because the Y is a predicted value. Now, when we actually write the equation, we don't want to use X and Y unless we're saying somewhere that X represents the percentage of birds that are returning, etc. So instead, it's better to write it with some words in for those variables. We're predicting the percentage of new adult birds based on the percentage of returning adult birds. If we're asked to interpret the correlation coefficient, we're just going to write something like the last statement on the previous slide. Generally speaking, as the percentage of returning adult birds decreases, the percentage of new adult birds will increase. And lastly, interpret the coefficient of determination. That's the R squared value, and we would say something like 56% of the variation in the percentage of new adult birds. That's the predicted value here. In this colony can be explained by the percent of birds that are returning. Another question you might be asked is this model appropriate? So we see that it's linear, there's no outliers. That's the first thing we'd want to check. After that, we'd want to look at the residual plot. We want to see absolutely no pattern, a bunch of scatter here. This one's pretty good. When we write this statement, we'll say the model is appropriate. The residual plot shows sufficient scatter with no obvious pattern. And we also want to write something about that R squared value, which we went over in the previous slide. 56% of the variation can be explained by the model. So at this point, we have the regression equation. Let's interpret the slope in context. Slope is the one that's right next to the variable here. It's negative. For every 1% increase in the percentage of adult sparrowhawks who return to the colony, there's an expected decrease of 0.304 of new birds. Okay, so we need to rate something like expected, or on average, it will decrease by that amount. Interpret the y-intercept in context. The y-intercept of 31.934 is the expected percentage of new birds to visit a sparrowhawk colony when it doesn't have any birds returning from the previous year. Lastly, for this particular example, calculate and interpret the residual for a colony which has 52% returning birds and 11 new adults. So that's talking about this value right here. And we can start off by taking that 52% and plugging it into our equation. Okay, that's going to tell us how many birds we would expect to get based on this percentage returning. We'd expect 16 new birds. Instead, we only got 11. So our residual is the observed minus expected value. Observed is the actual value, that's 11. Expected 16, subtract them, we have negative 5 birds as our residual. Interpreting it, this colony has 5 less new birds than predicted by the least squares regression line. I drew this line of best fit here just so we can take a look at where they are. Over here, we can pick out certain points like 52, 16. That's on the same X value and it's pretty much right on the line of best fit. So you should be able to look at a graph and pick out which points are which, along with their residuals. In this next example, we have a scatter plot and a residual plot showing the association between a child's Gessel score. This is just the score on a test they get early in life to measure their development, and their age at which they spoke their first word. Okay, just as I had mentioned, we should be able to look at these two plots even without these labels here and match up certain points with their location on the residual plot. So first question, is the point for child 18 high leverage? That's this one down here. The answer is yes, it is. The reason it is because most of our data is over here. This is far away on the horizontal axis. When we write this out with our explanation, we say something like its horizontal location, which is far from the mean x value, gives it undue influence on the regression model. So what does that mean? Okay, that means that it's going to pull the line of best fit towards it. The line of best fit, or the regression equation, is much different with this point versus without this point, which makes it influential. And that's how we would answer a question like this next one. Same questions for child 19. Is child 19 a high leverage point? It is not, because it's pretty much right in the middle of all the data. As far as the x-axis goes, it's not unusual. It's very close to the mean x value. Is it influential? Here's another graph showing what all these regression equations look like with child 18. That was the one way out to the right there. You see we have this blue line. That's much different than the green one here. That's without either of these points. Okay, without child 19, it's that red one. So it's a little bit different. So I'm going to write kind of. That's never a good answer. You never want to say kind of. So instead we'll say, yes, it is influential. The least squares regression line is different with the point versus without it. Always pick one and explain it, justify it based on your answer. Sometimes instead of giving you the actual data, it's going to give you statistics on that data. So here in this example, we have information on the stock market change in January compared to the entire year. The explanatory variable is the change in January, and is that predictive of what the stock market is going to do for the entire year? So based on these 5 values, we can find the actual line of best fit. Slope first, that's given by b sub 1 for the slope equals correlation coefficient times standard deviation of y over standard deviation of x. We're just going to plug everything in here, and we get a slope of 1.707. We always have to find slope first because y-intercept uses the slope in the equation. So we're going to take this, we're going to plug it in here, along with that x bar and y bar. Okay, and we get y-intercept of 6.03. Also, just to note, every regression equation based on data, or just based on anything really, goes through the point x bar comma y bar. So now we have the slope, we have the y-intercept, we can write our regression equation, and we don't want to use x and y, so we would write it like this instead. Lastly, sometimes we're not going to get any data at all. Instead, it's just going to give us a computer output that's based on that data. So here we're looking at the percent of animal species in the wild that survive to breed again. Oftentimes it's lower after a successful year. We have a study of merlins, which are small falcons. It's taken from northern Sweden, and it gives us this output here. So to start, let's write the regression equation. First thing, figure out which one is explanatory, which one is predicted. A lot of times up top in the table, it'll say predicted variable is. If it doesn't say that, this is always the explanatory variable. Okay, so you're using that to find the other thing. So a regression equation is based on the y-intercept, which is the constant, and the slope, which is next to this explanatory variable. So the percent returning equals 266.07 minus that slope times number of breeding pairs. Interpret S equals 7.762. This is the standard error of the residuals. It's telling us on average, the data deviates from the line of best fit by 7.762 merlins. So if we took all those residuals, okay, we average them all together, that's what we would get. We see 2 R-squared values in this table, R-squared adjusted. We never use the adjusted one, use the regular R-squared one. And lastly, what is R? How do we know if it's positive or negative? Well, r is the square root of r squared, and we know it's negative because our slope is negative. So negative 0.864.